Emission Engineering presents Oil Refinery Safety, the Art of Furnace Operation, Part 2. Hello, today we'll talk about Tramp air and draft control. A widely spread misunderstanding and wrong habit in many fired heaters in oil refineries is to operate with higher draft than necessary. A lot of people believe that the higher the draft, the safer the operation. But we will give you some contradictions today because we are not sharing this point of view. So let's have a look what API is actually saying about the draft. API 535 May 14 says at the bridge wall, meaning at the entry to the convection section, the draft should be in a range from -0.1 to -0.3 millibar of negative pressure. If you look on the curve to the right, you'll see how the profile of the draft looks like in a fired heaters. As you can see on the graph to the right, the draft increases towards the bottom of the heater where normally the burners are located. The major reason why very often this operating envelope is not put into practice is that the alarm and interlock set points for the draft are too restrictive or literally not set correctly. For example, if the alarm for draft is already set at -0.3 millibar, the control room operator, of course, will try to stay away from that, operating at a higher draft, for example, -0.6 millibar. In this example here, you will see what happens if the draft is operated too high. The green curve to the right, where you operate at the bridge wall with -0.2 millibar, will result in a radiant section which is roughly 10 to 12 meters high into a furnace draft at the bottom where the burners are located at -0.14 millibar. This curve actually shifts to the left if you operate on a higher draft than necessary. So the draft at the bottom, instead of -1.4 millibar, will be -2 millibar, and this will result in a higher ingress of air into the heater, and that can be calculated because it is the square root from 2 divided by 1.4. So you can see that approximately 20% more air is ingressed into the heater on a higher draft. As fired heaters changes their heat demand more often, some end users came to the conclusion that they are going to implement an automatic control loop, losing draft and O2 content in the flue gas, to sustain their operation without a need for field operators adjusting the burner air dampers. But this can be dangerous, specifically if you want to operate on low excess air levels, like for example 10% and lower, at all times due to efficiency reasons. We will explain you also why. In both sketches you see a furnace equipped with a combined automatic control loop for draft and oxygen. Assuming the firebox is absolutely gas tight, there will be no tramp air, meaning all combustion air comes in through the burner. As an example, we consider the heat release to be 1 megawatt in that fired heater. 1 megawatt requires stoichiometrically approximately 1000 ohm cubes per hour of air. With a 20% of excess air, this makes it a total air required of 1200 ohm cubes per hour. As seen in case 1 to the left, when operated at design draft, the total of 1200 ohm cubes comes in through the burner as there is no tramp air. In case 2, on higher draft, the same thing happens, meaning the control loop guides 1200 ohm cubes of air through the burner, independent if you operate on lower or higher draft. The only thing which is different is the burner air damper opening, which is apparently more closed the higher the draft is. Here in the example, 80% open. Now let's compare the situation when there is tramp air present, which is most likely in all refineries, fired heaters the case. Case 3 to the left shows the setup just as seen before, but now with excess air. In the example, we assume an amount of 150 nom cubes of air coming into the firebox throughout the peephole, side port, or any other opening which is not sealed properly. Firing still 1 megawatt requires still 1200 nom cubes of air, but now assuming 150 nom cubes of air is not getting in contact with the fuel, only 1050 of air comes through the burner's throat. As a consequence, the air damper is closed more and only 5% of excess air left over for combustion in the burner, respectively in the burner flame. 5% of excess air is already pretty tight for a combustion process. Note that the excess air that you measure throughout the oxygen analyzer still shows 20%, respectively 3.5% O2, although the real excess air at the burner has gone down already to 5%, respectively 1% of O2. Let's see to the right in case 4 how this looks like at higher draft. The 150 nom cubes shift to 180, which leaves only 1020 nom cubes for combustion, meaning only 2% of excess air in the burner itself. At this level of excess air, you got to have already passed the CO breakpoint, meaning you may not only have problems with CO emissions, you may also run into problems with flame stability, because process burners for fired heaters are not foreseen to be operated at such low excess air levels. Again, also in this scenario, you might see 3.5% of O2 at your oxygen analyzer, thinking all is alright, while it is not. Specifically, if your O2 analyzer is located downstream of the convection section, you may see higher O2 contents than what you have got on the burner in reality. Therefore, O2 analyzer should be placed upstream of the convection section. What you can see in case 4 as well is that the burner air damper is even more closed, in the example, to 60% open. The higher you operate the draft, the more you are obliged to close that damper. The more you do that, the tougher the change in flow rate will occur for the same change in percentage of damper change, which finally makes it even more difficult to adjust the design excess air of the overall heater. The more Tramp air one suspects in a heater, the more careful one must be applying this control strategy. What does the rulebook actually say how to control a fired heater? You'll see that on that slide here. The draft is controlled in the correct envelope by a classic closed control loop with a flue gas damper, and the O2 control is done manually by changing the burner air dampers. If you have automated burner air dampers, you can put a closed O2 control loop on those, but you should not combine O2 with a draft control loop. If you still do so or plan to implement this because your arguments are A. We don't have enough personnel for burner adjustment, especially if the furnace load changes more often, or B. You have to cut or you plan to cut back personnel anyway, or C. Your personnel complains to be too busy with other equipment, then in our opinion you would need to reconsider your safety procedures, because you are not only implementing just one more control loop, you are affecting the safety more than you may think on a first glance. We at Emission Engineering would be glad helping you in approaching safer operation without sacrificing the availability of your fired heaters. Please contact us at any time. Thank you. Emission Engineering. We engineer your emissions.